In this video, we're going to learn how to sketch polar curves. We'll start with a circle, expand to a spiral, explore a sinusoidal loop, turn that into a rose, and finally, we'll do the cardioid. Before we start, if you don't know how polar coordinates work, you can check out my previous videos linked in the top right corner, or find it in the description below. For this lesson, the Cartesian plane will be on the left, and the polar plane will be on the right. Let's start with the equation r equals 2. We map it on the Cartesian plane, where it's a flat line. When our angle theta is 0, the Cartesian graph tells us that the radius is 2. So on the polar plane, we draw a vector at an angle of 0 with a length of 2. As we sweep through all the angles, that radius stays at 2, tracing out a circle. If we change the radius, the Cartesian line shifts and the polar circle shrinks or expands. Now let's move on to a harder equation, r equals theta. This creates a slanted Cartesian line. We start at the origin of the Cartesian plane, which also happens to be the origin of the polar plane. We move to an angle of pi by 2, and here r is equal to 1.57. So we draw a vector on the polar plane with an angle of pi by 2 and a length of 1.57. At the tip of this vector, we plot the point. And then we move on to an angle of pi, where r is equal to 3.14. We draw a polar vector at an angle of pi with a length of 3.14, and at its tip, we place the polar point. We then move on to 3 pi by 2 and repeat the same process to get the next polar point. Finally, we move on to 2 pi to get the final point for our sketch. Now we connect these polar points to create our sketch. But right now, the sketch doesn't look very good. It's supposed to be a nice spiral shape, but it looks jagged. This is because we only sampled 5 points from the Cartesian to the polar plane. So we must sample 4 additional intermediate points from the Cartesian plane and transfer them to the polar plane. Now the spiral shape looks much better, but it would be even better if instead of joining the points with straight lines, we drew a smooth curve. So let's go back to the beginning and draw a smooth continuous curve through the points. Instead of transferring points directly from the Cartesian to the polar plane, we could have made a table tabulating the r values at various theta values and then plotting them on the polar plane. But in this tutorial, we will be skipping the tables. We can also change the coefficient of theta, which reduces the slope of the Cartesian line and reduces how far out the polar spiral extends. Now we move on to a sinusoidal Cartesian function. But notice that from pi to 2 pi, the r value is negative, and we want to avoid plotting negative values. So we should reduce our upper limit to just pi. We start at the origin of both the Cartesian and polar planes. Then we move to an angle of 0.12 pi, where r is 1.15. So the vector on the polar plane has a length of 1.15 at an angle of 0.12 pi. And we transfer this point from Cartesian to polar. Next we move on to pi by 4 and transfer the point again. We continue to do this for many other sampled points along the curve. Now we shall go back to the beginning and create a smooth sketch that passes through all of the points. We can change the coefficient of the sine function to adjust the amplitude on the Cartesian plot and the radius of the lobe on the polar plot. Remember how we ignored the domain from pi to 2 pi earlier? Now let's plot the equation in that domain. As you can see, the red plot from pi to 2 pi completely overlaps the blue plot from 0 to pi. And this is why we usually ignore it. Now, let's increase the coefficient of theta from 1 to 2. This increases the frequency of the Cartesian sine curve and changes the polar plot into a 4-lobed structure. Here the red plots no longer overlap the blue plots, and so we must consider the full range from 0 to 2 pi. If we increase the coefficient to 3, we get a 3-lobe structure. And this happens because the plots from pi to 2 pi once again overlap exactly with those from 0 to pi. To show this clearly, we draw a green plot from 0 to pi. And now we draw a purple plot from pi to 2 pi to prove that the two plots overlap. Now we move on to the famous cardioid shape, which is actually just a sine curve that has been shifted upwards so that its minimum value rests at 0. We perform the same process of sampling and transferring points, just like we did before. Once we have our points, we connect them to reveal a smooth cardioid shape. It's called a cardioid because if you were to flip your screen vertically, the shape looks like a heart. The first parameter is this green constant over here. And the second parameter is this purple coefficient. By increasing the green constant, we pull the polar curve away from the origin and puff it out into a rounded shape. By increasing the purple coefficient, the Cartesian wave now dips below 0, and it forces the polar curve to pass through the origin, creating an inner loop. We now know how to sketch polar curves. In a future video, we will also learn how to calculate the area of these polar curves using integration, so make sure to watch that next. If you found the video helpful, consider supporting my channel by liking, commenting, subscribing, and hitting the bell notification icon.